Welcome to the Proverbial channel, season 3, episode 36, the episode which I titled A Vicious Circle or Lords of the Ring, because in this episode we will construct a beautiful algorithm that will allow us to detect whether a given linked list contains a cycle or not. But before we deep dive into the underlying computer science, mathematics, and physics, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence. Thank you for subscribing to our channel and welcome to our channel. And second of all, perhaps the most efficient way for you to gain the most academic benefit for yourself from working with the material that we present on this channel is for you to go to the homepage of our channel, and at the top of that page, in the channel's trailer section, find the episode titled The Problemless Channel How To. We recommend that you watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. If you have any questions, then by all means do ask. The best way to ask your question is to find an episode on this channel that is of interest to you and use the comment section under that episode, and I will take it from there. And of course, and as usual, I would like to extend my deepest gratitude to all the current supporters and the current subscribers of our channel. The objective of the computer science problem S3CS8 is to construct an algorithm that will allow us to detect whether a given linked list contains a cycle or a ring or not. That is, a traditional linked list is a structure that is pronounced linear in its fashion, where each node in such a structure points to a unique address in memory. Such a correct linked list is represented with a structure shown on top over here, and it may so happen that through a not so careful manipulation of such a list, which by the way does not contain any branches and does not contain any cycles or rings, does have a cycle or a ring, which happens if one of the nodes in such a list points to a previous node in that list. In that case, if that was the outcome of the manipulation, of not so careful manipulation of this list, some number of nodes shown over here on the right side of the screen will be totally lost. This will be called a memory leak. But the objective of the algorithm that we are asked to construct in this case is to recover at least 3 units of information. First unit of information that our algorithm is expected to recover is a Boolean indicator whether the given input linked list contains a cycle or a ring. And this can be done by returning the address of the node to which 2 nodes in such a list point. And pretty soon in the next segment, in a few seconds, we will refer to this node as the origin of the ring or the origin of the cycle. That is one unit of information. The second unit of information is the following. In such a list, in its most generic fashion, we will have some number of nodes in that list that are not the part of the circular structure, that are not the part of the ring. And this linear or not broken stretch of the linked list has some number of entries, let's say n, and we want to recover that number, the number of the nodes in the list that are not part of the ring. And the third and the final unit of information is the size of the ring or the number of elements, the number of nodes in a ring. That is correct. The point of the show that you just saw was to demonstrate the fact that sometimes not only we witness, but we may actually participate in an event that may be a model for a solution of a technical problem, and that is what separates creative people from not creative people, because two such people, one creative person and another non-creative person, will look at one and the same thing, and a not creative person will shrug his or her shoulders and walk by without even realizing what they just saw, and the creative person will spin what he or she just saw 7 ways to Sunday creatively into a solution of a technical problem. And famously, the Swiss-born mathematician Leonard Euler was an absolute master craftsman of doing just that, taking a seemingly childish observations but lifting them with his technical ingenuity off the ground into the heights of something that is not trivial at all. And the point of this exercise is to show that we should pay attention not only when we are standing by the blackboard with a piece of chalk in our hand and doing academics, but in real life, committing certain things to memory and then being able to connect or yank this information out of web of your personal knowledge and connect what you have, the problem at hand, with what you know, and splice these two units of information into a solution of the problem. Here is a short quiz for you to see if you understood what I just said. Here is a model of a, let's say, a vehicle. This is a toy. And not only as a parent you bought such a toy for your kids, you played with the kids with this toy. And the question is, what is it? This is an event that not only you witnessed, but you participated in. What is this? Well, the short answer is this is a model of the so-called Klein 4 group, because cars have tires. The traditional four-wheel car has 4 tires. Tires wear out, and in order to make sure that these tires wear out evenly, we perform on a regular basis. What we perform on a regular basis is so-called tire rotations, and the tire rotations under the operation of composition, which naturally follows in real life. We drive a vehicle for 6 months, let's say. We flip the tires on this vehicle, drive another 6 months, flip the tires on the vehicle, and the tire rotations on a typical four-wheel vehicle under the operation of composition form the so-called Klein 4 group, designated with K4 or V4, depending on who you ask. In our particular case, the event of interest in which you may participate or which you may witness, most likely you witness quite a bit of those, could be car racing, horse racing, dog racing, speed skating, bicycle racing, and the various forms of on-foot racing. Closer to home yet, in this episode, the idea that we actually touched several times will be culminated in the construction of the sought-after algorithm, and that is in order to trace the genesis of this idea. In the computer science problem S3CS3, which we solved in season 3, episode 15, we honed in on the so-called Janus sort, which sorted in a linear container in an array only 2 types of objects. We put all the zeros, let's say, on the left of the array and all the ones, however many they are, on the right. And before we honed in on this idea, we stepped through these 2 Euler style or Eulerian baby observations. First, we observed that when we reverse the characters in a string, we technically employ 2 runners, one, let's say, right runner and the left runner. The left runner starts from the left extreme of the array, the right runner starts from the right extreme of the array. They both move towards the perceived vertical axis of symmetry of such a string. And it is important that due to the nature of the operation that we're expected to perform in this case, the velocities of both runners were the same, 1 entry in the array at a time. Also, we notice that in the test whether the given linear container constitutes a palindrome or not, we employed exactly the same idea. Instead of swapping elements at the equidistant from the proverbial or the logical vertical axis of symmetry of such a container, we simply compare them. But even that comparison is done with the help of 2 runners. the left runner and the right runner, they both again start from the opposite extremities of the container and move towards each other at the same rate. The velocity of the left runner is equal to the velocity of the right runner. In the string reversal case, in palindrome test, the same exact thing. The velocity of the left runner is equal to the velocity of the right runner. But when we came to the actual construction of the Janus Sort algorithm, we realized that the equal speed is not going to cut it anymore. So here we still have two runners. The left runner starts from the left extremity of the input container. The right runner starts from the right extremity of the input container. Both of these runners move towards each other, but this time the velocities of these two runners are not the same and they are conditional. Likewise, in a slightly more sophisticated problem, in the computer science problem S3CS7, which we solved in season 3 episode 31, we were asked to construct an algorithm which can detect whether a given input integer can be represented as a sum of two integers in an already sorted array. In other words, if the input integer I can be represented as x1 and x2, and x1 and x2 are both the elements of the input array that is already sorted in, let's say, ascending or descending order. It doesn't really matter. Here, how did we solve this problem? Again, we solved this problem by the introduction of two runners. The runner who started its journey on the left side of the container, and the right runner who started its journey on the right extremity of the container. Both such runners move towards each other, but here again, it so happens that the velocities of the left and the right runner are distinct. One takeaway from this episode, among other things, is that by analogy is a mighty powerful tool, not only in mathematics and physics, but in computer science as well. And you've heard it many times on this channel before, and you will hear it on this channel many times in the future when I say that the Swiss-born mathematician Leonhard Euler was an absolute master craftsman of taking seemingly childish observations and using the idea of by analogy in order to develop this childish idea into something that is meaningful, non-trivial, and quite deep. Back then in the 1700s, of course, Euler may have operated not as rigorously as we would like by now, but more than 200 years later, unleashing all the rigor on Euler's ideas still yields exactly the same result, which means that Euler's nose was always on the money. One of such famous examples is the decomposition of the trigonometric function of sine into what's called an infinite product. By today's standards, we think that Euler was a little bit fast, a little bit loose, but again, if we use all the modern rigor and construct an argument that is watertight by the modern mathematical standards, we obtain what? We obtain exactly the same decomposition of the trigonometric function of sine into an infinite product as Euler did back then more than 200 years ago. And on this channel, we will do precisely that. As such, by analogy here in the computer science problem, we will do the following. In its most general case, we will assume that if our linked list is broken and contains a cycle or a ring, then in its most general structure, we will assume that several nodes in that list, starting from the home plate or from the head node in such a list, form a linear structure or a classical linked list, if you will. In this particular case, we will have how many such nodes? 1, 2, 3, 4 nodes that are not corrupted, if you will, coming up to this node right here. And this node we will call the origin of the cycle or the origin of the ring. And then again, logically, it will so happen we can portray it in many different ways. This is just a logical portrayal. This is obviously not how things look in memory, but for our visual understanding of how things unfold, we will represent such a cycle in the circular manner. And again, this point will be called the origin of the ring or the origin of the cycle, and the number of nodes that are in the ring will be the ring size. We will, let's say, designate it with the uppercase N, and the distance HO from the head node of the list to the origin of the ring will be N. And again, in this algorithm that we're about to construct, This is the 3 units of information we want to hunt down. We want to know the address of the origin node, if it exists. We want to know the linear size of this not broken portion of the linked list, and we want to figure out what is the ring size, or how many nodes form that ring. To that end, and by analogy, we will also introduce 2 runners in our algorithm. I like to think about them as velociraptors for some reason, or just raptors, but you can think of them in any which other way. But the idea here is the following. By analogy with the previously solved computer science problems, we will introduce 2 runners. One runner will be called S for slow. This runner will move, let's say, at unit speed, or 1 node per unit time. And then we will have a fast runner who will be moving at twice the speed of the slow runner. In other words, this guy will step at the rate of 2 nodes per unit time. And once we have this information on the books, here is a short quiz. If 2 such runners start at one and the same point on the ring, let's say over here on this simple node, and they're off the blocks, off and running, let's say from this node, then by the time the slow runner makes or completes 1 full ring, 1 full circle, how many circles will the fast runner complete? That's right, this is a key observation. The fast runner will complete 2 circles. Because I wanted to make sure that the members of the audience pay attention, I purposefully made a small mistake over here. What is it? The small mistake over here is the following. If we partition all the nodes in our list into n, the number of elements in the node that contain or can form a linear or non-corrupt portion of the linked list, and the uppercase n in the size, then can this be correct? No, this is not correct. The correct answer over here is that the distance from the home node of the linked list to the origin of the ring must be n minus 1. So this over here is not correct. This brace has to terminate right here. This is the correct way to do it. So now, by analogy with our 2 raptors running around the ring, and this is already, I hope you see, why did I name this episode A Vicious Circle, or Lords of the Ring. We should be able to understand why the motivation behind this name. We now move into the computer science territory, and we introduce 2 pointers. We will operate in terms of pointers too. So our slow pointer will operate at which rate? The slow will be equal to slow arrow next. This is how the slow, we will implement our requirement that the slow raptor moves at 1 node of the linked list at a time, 1 step at a time, and then the fast pointer will move as follows. It will be fast, next, arrow next again. You see, this is how we implement twice the speed. If this is the unit speed, this is twice the speed of the unit speed. So the fast runner runs twice as fast as the slow runner. So now here's the question. Let us pretend that for the purposes of this thought experiment, our linked list was not manipulated too carefully. It's broken. It contains a cycle or a ring. And both of our raptors or both of our runners are off the blocks from the home plate or from the head node of this linked list. What is about to happen? How these guys will move? Well, let's do this experiment together. So let's say we have our slow runner and a fast runner. After the first step, the slow runner will be here, but the fast runner will be here. The fast runner will be here. Then in the next moment of time, the slow runner will jump over here, and the fast runner will jump 2 nodes over here. He will be already, or she, already at the origin. Next step for the slow runner, this is where the fast runner will be. And when the slow runner arrives at the origin of the ring, then where over here will be our fast runner. And precisely because the speed of the fast runner is twice the speed of the slow runner, what will happen if this distance over here is n, or in this particular case, let's count, we'll have 1, 2, 3, 4 nodes. How many nodes away from the origin will the fast runner be at the point where the slow runner is over here? Let's say we designate slow sitting right here, fast is right here. How many nodes? 1, 2, 3, 4. And this is quite obvious. It should be understood by everyone in the room. That's precisely because the speed of the fast runner is twice as much as the speed of the slow runner. Whatever number of units of distance the slow runner covers, exactly twice as much the fast runner will cover. And now we have the following question. If this is the case, if this is our starting point, or let's say t0 equals 0, this is our starting point, and we now let the slow runner start from the origin and the fast runner start from the node where it is at the moment. Here is the question: where will these two runners meet for the first time? Here's how most of the students will answer this question, which is to say, here's what an average student will do. And when I say average, I do not mean to belittle anyone. This is just how things work out statistically in the classroom. And I will purposefully not say the interesting words that are a hint right now. I will say these words a little later, but essentially, let's say that the node at which these two runners will meet will be designated as X somewhere on this ring, and this is what most students will say. We know that the distance covered by the slow runner as it runs to its rendezvous point with the fast runner. Remember that in the very first animation that I showed you, it does happen when the first runner is slow and the second runner is faster, definitely faster than the slow one. Eventually, they will meet on the ring somewhere. There will exist a rendezvous point where in a finite amount of time, the two runners will step onto one and the same node of the list that is bent into a ring. So here, that distance, let's say the distance covered by the slow runner will be the speed of the slow runner times the time tau that it took the slow runner to get to that rendezvous point. And at the same time, the distance that will cover the fast runner will be what? The velocity, or the speed, in this case, the constant speed of the fast runner times the same tau, the same time tau. It is important to understand that in this case, there are no integrals, no derivatives. We just use constant velocity. So this baby middle school formulas work. So what is the commonality between these two formulas? Well, the commonality is the time that both of the runners spend while getting to their mystery rendezvous point on the ring. So we will capitalize on that fact. From either of these two formulas, we know that since tau is one and the same, it follows what? That the distance covered by the slow runner divided by its speed will be the same as the ratio of the distance covered by the fast runner divided by the speed of the fast runner. But we know the ratio between the speeds of these two runners. This is how we constructed this. We know that the velocity of the fast runner is twice the velocity of the slow runner. Consequently, from this and this, it follows what? It follows that the distance covered by the slow runner divided by its speed will be the same as the ratio of the distance covered by the fast runner divided by two speeds of the slow runner. The velocity of the slow runner cancels out on either side of this equality, and what do we have? Twice the distance covered by the slow runner is equal to the distance covered by the fast runner. So let's say we designate the distance that was covered by the slow runner as x, what will we have? So let's say if we say that the distance covered by the slow runner is x, then according to our formula, 2 times x will be what? Well, let's think about it. Remember, we saw in the first animation that while the slow runner makes 1 complete revolution about the ring, the fast runner will make 2 revolutions. So what does that mean? Well, it means that our fast runner, if the slow runner is playing the catch up behind the fast runner on the ring, the fast runner, when they rendezvous at their point x, meaning the fast runner and the slow runner, the fast runner will make 1 complete revolution. So it will cover n. Remember that n is what is n? N is the size of the ring, or the number of nodes in that ring. And in order to partition our ring into these sizes correctly, we had to say that the distance, the non-corrupt portion of the linked list, or the classical linked list, has n nodes in it. We do not count the origin of the ring. The origin of the ring, as the number of elements in that ring going into which budget? It goes into the budget n, uppercase n for the ring size. So n plus n, lowercase n plus uppercase n, is the total number of nodes in such a crooked or corrupt linked list that contains a cycle. So what does that mean for us? For us, that means that the fast runner will make 1 complete revolution, over the ring, if it exists, if we temporarily assume that such a ring exists, and then it will do what? It will cover this distance right here. Let's say they meet somewhere at this node right here. Let's say this node right here. And what to this distance covered by the fast runner, what do we have to add? If this entire distance is x, and this distance right here, look at this distance right here, this distance was what? It was n. Remember, we proved that because the fast runner moves at twice the speed of the slow runner, if the fast runner gets over here, if the slow runner gets to here, then the fast runner gets to here. So this distance of n nodes in the list that are non-corrupt will be exactly this distance from the origin to the fast runner. And what does that mean? That means that the extra distance, this right here, that our fast runner will cover, will be given by what? It will be given by the entire distance x covered by the slow runner minus n. So it will be plus x minus n. Once we solve this trivial equation, we have 2x is equal to uppercase n plus x minus n. 1 copy of x and 1 copy of x cancel out. So from here it follows that x is equal to n minus n. This is our answer to the node where the 2 runners will rendezvous for the first time. But if we reshuffle this equality over here, let's say we move x to the right hand side of the equal sign and n we move to the left hand side, from here it follows what? That n is equal to lowercase n, uppercase n minus x. And what is n minus x? If this whole thing is n minus x, so this distance right here must also be n. You see the beautiful symmetry? This distance n and this distance n also. This follows from this deduction right here. And of course, once we come up with the theoretical argument, what do? We need to make sure that if we conduct this experiment with specific numbers, the specific numbers will work out. So let us do this experiment together. If you want, you can fast forward. You don't have to watch me do that. But if our slow runner steps over here, the fast runner gets over here, the slow runner is here, The fast runner is here. This is slow. This is fast. 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 This is slow. This is fast, and then this is slow, and this is fast right here. So this is the point where the two runners rendezvous for the first time. Let's designate them with both S for the slow and F for the fast. So this is the node where our runners will rendezvous for the first time. So if we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 nodes on the 12 nodes forming a ring, and we have 1, 2, 3, 4 nodes for n. So what is the answer for that node number over here? Well, it's our arithmetic, our mathematics tells us that it's 12 minus 4 is going to be 8. So let's count it. 1, 2, 3, 4, 5, 6, 7, 8. Bingo. In this particular case, the specific number is 8. It doesn't really matter in the big scope of things, but our mathematics converges, our theory converges with practice. This is what we deduce by unfolding a so-called deductive reasoning. But now here is the thing. I hope to think, or like to kid myself, that on this channel we do not grow, or we do not nurture average students. We nurture above average students. And here is the hint for a different or an alternative answer to the question that we posed earlier. What is the node on which the slow and the fast runner will rendezvous again for the first time once they're off the blocks, to how this question can be answered creatively? And here is the hint for you if you still want to give it your own shot. What happened over here is the following. We came up with this whole line of reasoning right here. This entire line of reasoning was generated by what? Was generated by the forward flow of causality, if you will, or the forward flow of time. What we did over here, and this is how, again, this is why I say most students will do that. And there is nothing wrong with this line of reasoning. This line of reasoning is correct, but on this channel, this line of reasoning is not creative enough. Fundamentally, this line of reasoning is based on the following idea. What will happen in the future? What will happen in the future if the slow runner S starts from the origin and the fast runner F starts from this node right here? If you joined our channel after season 1 and season 2, then you definitely missed something. But in this respect, I have two types of news for you: the good news and the even better news. The good news is that you still have a chance to go back to season 1 and season 2 and work your way through all the episodes on this channel where we studied all the popular 10 problem-solving approaches in a highly focused, highly dedicated manner. And the good news for you is that the reverse order problem-solving approach, which we will use right now in order to answer the posed question, was covered in the following episodes: season 2, episodes 3, 4, 5, 6, 7, 8, 9, 10, and all the episodes that are dedicated to the focused study of this problem-solving approach, called reverse order or reversed time flow, are put together into the playlist called the reverse order. And the even better news is that you can study all this material at your own pace, at your own leisure. You have this information available to you free of charge, and we recommend that you do that. But here is the thing, coming back to our solution that we just developed a few seconds ago, most students in the classroom will fundamentally shuffle the symbols that we showed over here, and they will arrive at the correct answer. There is no argument there. They will arrive at the correct answer, but they will shuffle the symbols based on the answer to the following question: what will happen in the future if? In other words, here we conduct the following thought experiment. Let's say our slow runner S and the fast runner F run over the vicious circle for eternity at the rates that, at the speed rates that are locked in. And they do so, let's say, counterclockwise. They run and they run, they run and they run. And then in some perhaps quantum mechanical sense, we decided to take a look-see. What is going on with this system? Well, famously, the wave function of the system, that is in the superposition of all states, collapsed into something that allows us to uniquely identify and describe the structure of what is going on. And at that moment of time, we see the slow runner S at the origin of the ring and the fast runner F sitting over here at this particular node, under the assumption that the structure of this linked list, broken linked list that contains the cycle, is what it is. See, here is the difference between a creative and non-creative solution, even though non-creative solution is technically still correct. A non-creative solution will shuffle symbols based on the following idea. What will happen in the future if we let the slow runner S and the fast runner F run forward and let the time flow forward in the traditional flow of causality, flow forward of time. But the creative solution that actually does not shuffle any symbols, in the answer that we're about to construct, there will be no symbols, no equations to manipulate. Here we assume that in most cases, time can flow in both directions, especially when it comes to physics. As far as I'm aware, pretty much all the equations in physics where time comes in, there is no restriction, there is no hard mathematical restriction that the time must flow forward only. The time can flow in reverse, so the time can flow backward. So here, once our slow runner and the fast runner run for eternity and over the vicious circle with the locked-in rates in the quantum mechanical sense, boom, we freeze the system, we take a look-see, everything comes into this position. The slow runner S is at the origin, the fast runner F is at the point where it is. Here is the difference between the creative and non-creative solution. In the creative solution, instead of thinking what will happen in the future, we already claim that this state is the future. And the interesting thing to us is the following: what happened in the past? And in the past, we already proved with mathematical inevitability and precision that these two runners rendezvoused at some point X. And what did happen at that point X? Well, if we let the camera roll, if you will, forward in the forward flow of time or in the forward flow of causality, our runners took off the blocks over here from the point X. The slow runner moved one step at a time, one node at a time, and the fast runner had moved at twice the speed and two nodes at a time. But this is very important to realize, that instead of basing our answer on what will happen in the future, we already assume that this is the future, and we develop our answer based on the question what happened in the past where the two runners met at the point X. And at that point, a very interesting thing happened, which I said these words at the beginning of this episode. But remember, if the slow runner covers the distance x, it doesn't matter, covers distance x covered by the slow runner, then how much distance will the fast runner cover? 2x, exactly. The fast runner will cover the distance 2x. So let's count this. So this is the slow runner. Slow runner makes one step, the fast runner steps over here. The slow runner gets here, the fast runner gets here. The slow runner gets here, the fast runner gets here, and I want to make sure that you guys see it. The slow runner gets over here, and the fast runner, boom, happens to be over here. What is the distance that the slow runner covered? X, there it is. And what is the distance that the fast runner covered? 2x. And what does that mean? It doesn't really matter over here that our trajectory of the two runners is wrapped into a circle. Let's say they started running in a linear fashion. It doesn't really matter. So starting from this point, d is the distance covered by the slow runner. The fast runner is over here. He covered, this is another distance, d. The total distance is 2d. Remember, twice the distance. So what does that mean? That means that the point x is located from the point S, where the slow runner is, by exactly the same distance that separates the slow runner and the fast runner at that moment. Simply we flip the distance back and boom. So in this case, in order to answer this question without any formulas whatsoever, but reasoning in the reverse flow of time fashion, if we sort of recorded the movie of these two guys running, and then at that point the movie stopped, and now we're playing it back. So the slow runner steps into this point, and the fast runner goes here. The slow runner steps from here to here, and the fast runner stops from here to here. And then the slow runner gets here, the fast runner gets here, and then boom, they both converge over here. This is absolutely beautiful reasoning, and this is what separates creative people from not creative people, or creative solution from not creative solution. So in order to answer the posed questions, all we have to do is, let's say if our runners run counterclockwise, measure the distance from the point S that separates S and F in the clockwise, in the opposite direction. So if this distance is 1, 2, 3, 4, then the point X where these two guys rendezvous must also be 1, 2, 3, 4 units away from the origin, but counted or measured, if you will, counterclockwise. Wonderful. Now that we proved that the node X, or the point where the two runners will meet on the ring for the first time after the slow runner is located at the origin of the ring and the fast runner located on the ring somewhere over here, has exactly the same distance from the origin as the home plate or the head node of the linked list. In other words, the distance from here to here is the same as the distance from here to here. We want to answer the following question: how do we recover the address of the origin, or how do we recover the address of the node to which two nodes in this broken linked list point? Well, the answer to this question explains the second part of the title of this episode, Lords of the Ring, where here I suggest that our viewers recall the scene from the movie called Jurassic Park, where the Dr. Grant is schooling a little boy about being respectful to the habits and the intellectual capabilities of the dumb birds that the velociraptors are. And the two velociraptors, you did not even know they were there. In other words, once our runners, two velociraptors, converge on the point X as S and F, we keep one of these raptors at the point X, but we put the other raptor into the home plate, and now we'll let them converge on the innocent victim on the origin O from two different directions. But think about the speed of these two raptors at this point. Before, they were running at the rates the fast runner was twice as fast as the slow, but this time we'll let the two raptors converge on its innocent victim from two different directions. How? At the same rate, at the same speed, because they right now, if the distance, we already proved that the distance from the node X, from their rendezvous point to the origin of the ring, and the distance from the home plate to the origin of the list is the same. So if they move at the same velocity, then they will get to the origin at the same time. So one step at a time. 1, 2, 3, 4. Boom. The two raptors converged on its innocent victim, and by so doing, we identified the address of the node. In other words, translating this wonderful Jurassic Park and, by analogy, velociraptors, the whole thing, into computer science, we will say that how we will write the code. Well, we'll say that while, let's say, slow is not equal to fast. Look at this. This is another beautiful implementation that is ported nicely from the analogy into the actionable computer science. Let's say we keep the fast runner at X, we put the slow runner into the home plate, into the head node of this list, and we let the slow runner advance one node at a time in this direction, S guy from here, the F guy from here. Then we will say while the fast runner, the address of the fast pointer is not the same as the address of the slow pointer, what we will do? Well, slow will advance one node at a time, next. And fast will advance also one node at a time, next, like so. And also, what can we do while we do this? Well, while we do this, we can count n. We can count n. So if we do our proverbial n plus plus, where we initialize this guy to 0, then we will also count the number of the nodes in this list that form a linear or non-corrupt segment. And in our previous loop, while the chase was going on, while these guys are not meeting, we will count the number of nodes in the ring. And at this point, I hope that you guys understand my justification for the title of this episode, a vicious circle, because this is how we detect a circle or a ring, if you will, a cycle or a circle or a ring in the linked list. And the reason I put the lords of the ring is precisely because the means of how we do it, how we detect the presence of a vicious circle in our linked list. Well, by using two runners in two stages. In the first stage, our runners run at the varying rates, even though they start from the same place, from the head plate or from the home plate or from the head node of the linked list. And in the second stage, once they rendezvous over here, if they rendezvous, of course, if they don't, there is no ring. But if they do, then in the second stage, both runners will run at the same rate. Close curly, and here is another amazing thing that you will witness time and time again in computer science and elsewhere in mathematics, physics, theoretical physics, is the following. Once a successful idea has been generated, the rest of the implementation of a seemingly difficult problem becomes a smooth sailing. And over here, it is really amazing how nicely all our ideas that we discussed in this episode unfold into, for example, the implementation of this algorithm in the best programming language of all times, C. And of course, we by now all understand that a computer science algorithm as its entity is totally separate from the host programming language that runs on the host operating system, that runs on a particular hardware with this set of chips and memory and this and that, yada yada. This is all completely separate and has nothing to do with each other, but we need to do something. And here we use the best programming language of all time, C. And our prototype is the following: find ring origin. This function over here, I did not have room, but it will be in the source code, of course. The link to that source code is in the comment section to this episode. Click, pop open the tab in your browser. This will take you exactly to the C file that is sits in my free GitHub repository. You can take it from there. But here, this function returns the node t, and the meaning of the return value is precisely the origin of return, the origin of the ring, if that ring is present. And the rest of the signature of this function is the following. On the input, we take the home plate or the head node of the list that is under suspicion, the size t star, the pointer to the variable that will store the size of the ring, and the pointer to the variable that will store the size of the linear segment of the link that is not corrupt. And here we need two frame variables only. We do not need anything else. Two frame variables. These are our proverbial raptors. The slow pointer and the fast pointer both are initialized to point to the home plate, to the home node of the list. We zero out all the sizes, no ring, and the contents of this variable in some sense do not really matter. But here our first portion, once we release the two raptors off the blocks and they start chasing, if the ring is present, this is how we do it. While the fast next pointer is not null, in other words, we want to see if the fast runner got to the end of the list before meeting the slow. That means that there is no ring, there is no cycle, there is no circle in this particular linked list. Everything is good, and we'll see it in a second. But here the idea is this: while fast next is not null, this is the tribal knowledge, the tribal idiosyncrasies of the C programming language, we will increment the number of elements here in the list. And we will say that the slow pointer is stepping one node at a time, the fast pointer steps two nodes at a time at twice the speed in. If it so happens that the slow is equal to the fast, in other words, the fast runner caught up and there is a link, then we break out of this loop. X marks the spot and we have a cycle. But if it's not the case, if this if clause never triggers, then the first thing that we will do after we come out from the while loop over here, we come over here and we test if slow is equal to fast or not. If it's not, then we will reset the number of nodes in the ring to 0, and we will return null, signifying that there is no ring, there is no cycle in this list. Otherwise, the slow is fast, X marks the spot, and remember what we did over here a few seconds ago. We kept the fast raptor at X and we put the slow runner at the home plate at the head node of the link. This is how we do it over here. Slow is equal to H, and then we roll our while loop, making or letting two raptors converge on the innocent victim from two different directions in a coordinated attack. Boom. And now we have it while slow is not fast. We increment both of these pointers at the same rate. Remember, at this point, the velocity of these velociraptors is exactly the same. They both move through the portions of the linked list at the same rate, or one node of the list at a time. We also keep tabs star n++. We also keep the tabs on how many nodes are in this list that are not corrupt and form a linear segment or a classical linked list. At some point, we know that in a finite amount of steps, this loop will terminate, and once we come out, boom, we have slow, or as I said, fast over here, pointing to the origin of that ring. We know what it is, and by returning a non-null pointer, we indicate right away that the contents of the other variables that are passed into the function, the contents of uppercase n and the contents of the lowercase n, are meaningful and can be looked at. So as a caller, you will say if not, let's say, find ring origin, then you'll do something else. Or if you can say if find ring origin, then you have non-null pointer on the return value and some meaningful numbers over here. Now, this is it for the computer science problem S3CS8, and we will move on to a new challenge next. Our next challenge will be the problem in mathematics S3M12, and in that problem we're asked to show that for all x real distinct from integral multiples of pi, in other words, for all x real not equal to plus minus n pi, where n varies 0, 1, 2, 3, 4, 5, and so on, it is the case that the value of the trigonometric function of sine evaluated at such an x can be represented as x times this here infinite product, where the product variable varies from 1 to positive infinity, and the common term of this product is the following: 1 minus x squared divided by n squared pi squared, and evidently starts varying from 1, 2, 3, 4, 5, 6, 7, and so on. This is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will present my solution of the mathematical problem S3M20.